A spring mass system. One end of a horizontal spring with force constant 130 newtons per meter is attached to a vertical wall. A 4 kilogram block sitting on the floor is placed against the spring, so here's the 4 kilogram block. The coefficient of kinetic friction between the block and the floor is 0.4. You apply a constant force F to the block. F has magnitude 82 newtons and is directed toward the wall. At the instant that the spring is compressed 80 centimeters, what are part A, the speed of the block, and part B, the magnitude and direction of the block's acceleration? Okay, so let's start with drawing a free body diagram of this block. We have to identify the forces acting on it. There will be the weight, the normal force from the horizontal surface. There is the force F we are applying to the left. There will be a spring force which is trying to restore the equilibrium length, Fs, and because the block is moving to the left, kinetic friction will be to the right. So let's plot the free body diagram. So in part A, here is the free body diagram of the block. Now we have the weight pointing down. Here is mg. Here is the normal force from the table pointing up, N. Here is the force F we're applying towards the wall, F. The spring force, and there will be kinetic friction, so we have to show two forces here to the right. So there will be the spring force and the kinetic friction. And setting up the coordinate axis here, since the block is moving to the left for convenience, I'm going to call this y-axis this x-axis. So y and x is pointing towards the wall. The net force on the y-axis must be 0 because the block is not moving on the y-axis. So normal force must be equal to the weight of the block, which is, the block was 4 kilograms. So it is 4 times 9.8. That's equal to 39.2 newtons. Then the kinetic friction is coefficient of kinetic friction times the normal force. The coefficient of kinetic friction was given as 0.4. So it is 0.4 times the normal force, 39.2 newtons, which is 15.68 newtons. The net force on the x-axis is equal to, in plus I hat direction, plus I hat pointing to the left here, I have the force F that I'm applying, and the restoring force and kinetic friction, force of friction, are both opposing this motion, and therefore I will have F minus kx is our displacement. It's proportional to the displacement x minus mu k times the normal force. So the force that I'm applying has a magnitude of 82 newtons. So this is 82. The force constant was 130 for the spring, so 130x minus 15.68 newtons, the kinetic friction, force of friction. So this gives me a total of 66.32 minus 130x, a spatially varying net force. Then what is the net work done on the system in carrying it from x equals 0 to x equals 0.8 meters? That's what we are doing. We're compressing it to 80 centimeters, which is 0.8 meters. This is the net force dot product with the displacement. The net force is to the left, the displacement is to the left, so integral 0 to 0.8, net force 66.32 minus 130x dx. This will give us 66.32x minus 65x squared, which is to be evaluated between 0 and 0.8. So this gives us, when we substitute x equals 0.8, 53.056 minus 41.6, which is 11.456 joules. Then we can use the work kinetic energy theorem. The work done by the net force acting on a system is equal to change in its kinetic energy. The final kinetic energy is 1/2 mv final squared. The initial kinetic energy is 0. So it was sitting on the floor, then we applied the force, so initially it was at rest. So the work done by the net force is 11.456 joules, and this gives us for the final speed as 11.456 times 2 divided by its mass, 4 kilograms, square root, and we have to reduce the answer to 3 significant figures, so we find the answer to be 2.39 meters per second when reduced to 3 significant figures. So basically we have utilized a work kinetic energy theorem to calculate the speed of the block when it is at a distance 0.8 meters from its original position. Now we're going to calculate the acceleration. So in part B of the problem, if I look at the net force on the x-axis when x is equal to 0.8 meters, so the net force evaluated at x equals 0.8 meters is now 82 newtons minus 130 times 0.8, so 82 minus 130 times 0.8 minus the force of friction 15.68. This gives me minus 37.68 newtons. So the minus sign indicates that now it's pointing away from the wall. So the net force is equal to mass times acceleration. Acceleration will be minus 37.68 divided by the mass, 4 kilograms. So this gives us minus 9.42 meters per second square for the acceleration. And we have found a negative acceleration here, which means that this is plus I hat, this is minus I hat. The acceleration is directed, it will be directed away from the wall. So it's not pointing towards the wall, its acceleration is directed away from the wall. Okay, so to summarize, we have a horizontal spring, force constant 130 newtons per meter, attached to a vertical wall. A 4 kilogram block sitting on the floor is placed against the spring, and then it is compressed by applying a force F. So this is the relaxed position, this is the compressed position, compressed by 0.8 meters. There is friction between the horizontal surface and the block. 0.4 is coefficient of kinetic friction. The force that we're applying is 82 newtons. We want to know the speed of the block and acceleration of the block at that instant in time. So when I look at the free body diagram of the block, I can calculate the net force acting on the system as F the force that I'm applying to the left, which I have defined to be minus plus I hat direction, minus the spring force minus kx, minus kinetic friction mu k times n opposing the motion. So the normal force is balancing the weight, so it's mg, so Fk is mu k times the normal force, and I find the net force, which is x dependent, 66.32 minus 130x. The net force in the minus I hat direction, the displacement is in minus I hat direction. I go from the displacement is plus I hat direction, net force is in plus I hat direction, which I have defined in the minus x direction. So this work done by this net force is x equals 0 to x equals 0.8, dot product of net force with displacement, which are all in the same directions. So we find that this net work done is equal to the change in kinetic energy of the system because it was initially sitting on the floor at rest. We find that the final speed is basically found using work kinetic energy theorem. And when we evaluate the net force acting on the system at x equals 0.8, it turns out to be negative. And as you can see, since I have defined this to be positive direction, negative is away from the wall, and acceleration turns out to be F net equals ma, Newton's second law, minus 9.42 meters per second square, which is directed this way, directed away from the wall.